We're going to go a little bit out of sequence here because our next topic, which is duality, which is a really big deal, deserves to have a week to itself. And so because we only have a little half-week slot to fill in, I'll skip over it and talk instead about some applications. So we've spent all this time talking about linear programs, talking about if somebody just hands you a linear program out of nowhere, how do you solve it? And I guess also, if somebody hands you some strange non-standard looking LP, how do you turn it into a standard one so you can solve it? But we really haven't spent that much time talking about where these things come from. So apparently people want to solve all these linear programs, but why? And we're going to spend a lot of time on applications going forward. And of course, some of the grad student presentations at the end of the semester will be about specific applications. But we do have to make some progress on that. We do have to provide some of that payoff of why were we doing all this stuff all along. And what I want to talk about today is a specific form of application. It's actually a couple of somewhat contrived problems, although one of them that I'm going to talk about in the second video is something that comes out of machine learning. But the first one is definitely a bit contrived. Problems that appear to have some sort of non-linear flavor, where you would look at them and think, I don't know that I can solve this with a linear program. But if we're careful, we can actually find some way to remove the non-linearity as far as optimization is concerned. So one thing that's important to understand is, if somebody hands you an application, there might be a way of solving an optimization problem hidden in that application using linear programming if you can find a way of removing all the non-linear elements in advance. And one typical example of that, I guess, would be to do some pre-processing to take care of any non-linearity. And the first application I'm going to discuss, although a little bit contrived, I think is a great example of that. And it is the largest disk in a convex polygon. So suppose that I provide to you a convex polygon specified as a list of points. And I also guarantee that the list that I provide, which is an ordered list, so 0, 1 up to n-1, is guaranteed to be an ordered traversal, a clockwise traversal of the vertices of the polygon. And the reason why it's important that they be provided in that order is that if I just provide the vertices in some random order, it might be hard to reconstruct the edges of the polygon. Whereas if I guarantee you that the traversal I provide is a clockwise traversal, well, the fact that it is a clockwise or counterclockwise traversal means that I know that, for example, if P0 and P1 appear next to each other in the list, then this line segment between the two of them must be an edge of the polygon. The significance of a clockwise traversal specifically, as opposed to just some traversal of all the vertices in order, is that we can also assume, and you may know this if you've worked with convex polygons before from a geometry standpoint, so in a computational geometry course or something. If I have the vertices in a clockwise traversal, and I walk around the polygon, so I walk between each vertex in order. As I walk forwards along each edge, at every step, the interior of the polygon will always be to my right if I have a clockwise traversal. If it were a counterclockwise traversal, I would always have the interior to my left. So as I walk around the outside of the polygon, if I'm guaranteed to have a clockwise traversal, I know that if I make a right turn, I'm always going inwards, and if I make a left turn, I'm always going outwards. And that'll prove to be a little bit helpful later. Obviously, in general, working with convex polygons, you can always take an arbitrary ordering of the vertices and turn it into this clockwise traversal using some computational geometry algorithms. But the reason we're not going to worry about that is that this isn't a computational geometry course. So we'll assume we already have that clockwise traversal of vertices. Now, one of the reasons I think it's great that we maybe left this application a little bit later in the course, I was thinking about giving this lecture as like lecture number 3 or something. One of the reasons I think it was a good idea to leave it is that, in a sense, what we're going to do with this application, so we're working with convex polygons for a geometric application, what we're going to do with this will essentially involve deconstructing a convex polygon using what we already know about things like half spaces. So we know by now that if I look at any convex polygon, you could view it as just the intersection of a whole bunch of half spaces. And so we're going to end up using a linear program to solve this problem that has a lot of similarities to a linear program itself, even though the problem we're solving has some suspicious non-linear aspects. So here's the problem. I provide you this convex polygon in the plane on this clockwise traversal of vertices, and I want you to find the center point and radius of the largest disk that can fit entirely inside the polygon. And the edges of the disk are allowed to touch the edges of the polygon, but no area of this disk is allowed to exceed the bounds of the polygon. So I want the largest disk that can be inscribed in the polygon. And to be clear, this is an optimization problem because of the word largest, obviously. That sort of gives it away. But therefore, maybe it's obvious to you that the radius clearly is one of our optimization variables. We're trying to maximize the radius of this disk. It's also important to recognize that the center point of the circle is actually an optimization variable, or in this case, I guess, two optimization variables. And the reason is because if we take a look at a convex polygon like this one, notice that there are lots of places I could stick a disk in the middle of this polygon. I obviously, depending on where I put it, I might be able to get a larger disk, to fit a larger disk into the polygon. So the center point is also something that could be variable. It is also one of the things that has to participate in the optimization process. Now, I skipped over this, but this problem is presented in one of our two books. It's presented in a completely different way. It's the same application, and I mean, fundamentally, the linear program that's produced is pretty similar once we sift away all the notation. I prefer the presentation in these slides, I guess, obviously, because I made the slides, because I feel like one of the benefits of looking at this application is seeing how pre-processing can help us eliminate nonlinearity. And I feel like the way that they deal with it in this book doesn't make that as obvious as it should be. So what I'm going to do here is I'm going to construct a bunch of vectors and then use those vectors to construct other vectors so that I hope that the steps of the solution are more clear. What they do in the book is make a bunch of observations and then sort of combine them all at the end, which is valid, but I don't think it demonstrates the point as well as I would like to. We'll see for the second application in this lecture, the way that this book covers it is not my favorite at all. Although for this application, they have a pretty sensible way of covering it. I just think that it's better to unpack it a bit more. It's worth noticing that if I have this closed convex polygon, the largest disk that I end up producing will always touch at least two sides of the polygon. Notice that in this example and in the previous one, it actually touches 3 of them. And here's an example where it touches 4 of them, and here's one where it touches 3 again. It turns out that the case where it touches 2 is sort of a degenerate case. It's something like a rectangle, where it can't reach a 3rd side. But it definitely will always touch at least 2. And the reason, I think, just sketching out the reason, maybe it's obvious, but if it didn't, if it only touched, well, first, if it touched 0 edges, if this was my largest disk, that would be ridiculous. That would be a contradiction, because clearly I can make it a little bit larger. If the disk only touches 1 edge, so if it bumps up against 1 edge, well, why don't I just move the disk a little bit this way and then make it a little bit bigger? So unless it's being squeezed between at least 2 edges, it makes sense that I could make the disk bigger, and that's why it's reasonable to assume it'll always touch at least 2 sides of the polygon. But of course, there's no requirement that it touch every edge of the polygon, and maybe it's obvious, but we could easily create in any convex polygon a whole bunch of tiny edges somewhere in one of these corners down here where the largest disk would never go anywhere near it because the corner pinches off any ability to construct a large disk in that area. So there's no requirement that the disk actually touch every edge or even a large number of edges of the polygon, but it will touch at least 2 of them. Assuming, of course, that we've got a non-degenerate polygon, so assuming that the polygon has a non-empty interior. If the interior is empty, then the radius will be 0. And so hopefully that's enough to justify that what I'm actually optimizing is not only the radius of this disk, but where it's located. I need to find a location to center the disk, and that could differ depending on the structure of the polygon. So going forward, what we have to acknowledge is that these 3 variables, cx, cy, and r, and I'm occasionally going to refer to the center point as being an optimization variable, but if I do that, I'm referring to both coordinates of the center point. These 3 things, cx, cy, and r, are going to be the optimization variables for this problem. We're going to see all sorts of other symbolic notations, so we're going to talk about P2 and P3 and things, but those are all constants. They've been provided in advance. As far as determining the largest disk, the positions of vertices are all fixed. And therefore, we're allowed to do whatever we want with positions of vertices. I could multiply them together, I could take square roots, I could square them, because ultimately I could just pre-compute that and then feed that into my linear program before I solve it. And it will be that way that we end up avoiding what might be clear to you is an apparent nonlinearity, which if we're talking about circles, that's already a bit suspicious, right? I mean, we certainly are aware that specification of a circle requires squares, and depending on how you phrase it, maybe also square roots. And also talking about parameterizing a circle this way with a radius and finding the largest radius that's possible seems to require some kind of distance calculation. So, for example, this is my center point. How do I know that this radius is viable? Well, I have to make sure that the distance between here and the nearest edge is less than something or doesn't exceed an edge. It seems like I need some kind of Euclidean distance calculation, which of course seems to require squares and square roots. So the question is going to be, how do we keep our ultimate optimization problem from requiring the use of nonlinearity? And the answer is we're going to pre-process it away. We're going to find some way of turning this into a pretty straightforward linear optimization problem by getting rid of all the nonlinear stuff in advance. So really what we're doing here is we're looking for a center point, cx, cy, such that the distance from that center point to the nearest edge of the polygon is maximized. And that distance will become ultimately will become this radius of that largest disk. So we have to be careful here. The distance to the closest edge is maximized. And what that really means is the minimum distance from this center point to any edge is as large as possible. So, and that maybe makes it even more clear why we have to have our center point be one of the optimization variables. And so we think, okay, but there's that word distance again. And if we define distance the usual way, so Euclidean distance, we've got a square root. And so the point of this application is to show how we can avoid actually needing a square root in the optimization problem by maybe a clever rephrasing of the problem in terms of vectors and particularly normal vectors for the edges of the polygon. And that's one reason why I think it's great that we already spent so much time on half spaces and normal vectors, because some of this will be a lot more natural to us now. So here's what I'm going to do. I'm going to start with our list of vertices, p0 up to pn-1, and I'm going to derive a couple of vectors as a convenience, I think, to sort of show the steps of this solution. Before I do that, I want to notice how in this traversal of vertices, clearly the polygon itself is cyclic. I can just keep going around the vertices over and over again. So as a convenience, what I'm going to do is I'm going to say this polygon has 6 vertices. They're numbered 0 through 5. We'll define P6 to just be P0 again. And that's helpful because that means I can talk about, for any value of I can talk about Pi and Pi plus 1. So we'll do that as a notational convenience. And now I'm going to define a vector. And as I've done in previous lectures, I'm allowing myself to treat a point in 2D as a vector for the sake of performing arithmetic. So I can subtract one point from another. We do the arithmetic component-wise, just like you'd expect. And I'm going to construct these vectors EI. And I'm realizing now saying this, I guess it wasn't obvious to me when I made the slides, I'm realizing saying this that yes, if you've taken linear algebra, E sub I might have a special meaning, but not today. I use the letter E to refer to the edges of the polygon. What I'm creating here is a vector parallel to each edge of the polygon. So we know that Pi and Pi plus 1 lie on a common edge of the polygon. What I want to get is a vector that describes the direction of that edge. And so we end up with these. Or we end up, this diagram is an abstraction. So obviously, because, for example, E1 is a vector, E1 isn't floating around here, like it isn't anchored at the point 2, x equals 2, y equals 3. E1 is just a vector. But if we draw it, to illustrate what it's meant to correspond to, which is that edge of the polygon, it has this direction and magnitude. And so what I now have, if I look at each of these vectors EI, I have a set of vectors that are parallel to each of the edges of the polygon, indexed to the lowest numbered vertex on that edge. So for example, this edge here, between P1 and P2, is described by the vector E1. What I want to do now is I want to define a normal vector to each edge. And we've seen before that, yes, although we can define half spaces and things in terms of vectors parallel to the boundary, it's often a lot easier, especially in 3 dimensions or 4 dimensions, but that's not the case in this problem. It's often a lot easier to work instead with normal vectors, vectors that are perpendicular to each to the boundary of the half space. And that's what I'm going to do here. I'm going to now derive an outward pointing normal vector for each of these edges. So when I say outward pointing, what I mean is that the vector always points away from the interior of the polygon. We should be familiar with the benefits of doing this because we're already aware in a 2D linear program, if I look at the constraint system and I try and determine the feasible region, we can consider each standard form inequality constraint as, in a sense, containing this outward pointing normal vector, where the points that are in the half space are the ones behind the normal vector. The normal vector points away from those. So I'm going to do that here. This is the formula to do that, and I'm not going to give a full derivation of this, although if you were to sketch it out, you would sort of see why this formula always works to get an outward pointing normal vector. But I will give a brief graphical justification. So I mentioned earlier, without proof, although this can also be proven, that if I am guaranteed to have this clockwise traversal of vertices, and I walk along each edge in the order, in the direction of that traversal, then at every step, the interior of the polygon is always to my right, and the exterior is always to my left. Now, the benefit of that is it means that if I rotate each of these edge vectors by 90 degrees to the left, so 90 degrees counterclockwise, I will get a vector that points, that's orthogonal to my edge and points outwards. I'm guaranteed of that because the property of the interior being to my right holds for every single edge. And without going into more detail, if I do that rotation by 90 degrees counterclockwise, this is the formula I end up with. So I take each vector EI, and then I define my normal vector, which we'll call VI, to be the negative y component of the edge vector, and then as the x component of my normal vector, and the x component of my edge vector as the y component of my normal vector. And it's pretty easy to verify that if I were to take the dot product EI dot VI, that I would get EIX times negative EIY plus EIY times EIX. And that if we stare at that for a minute, it becomes clear that that is going to equal 0. So certainly EI and VI are orthogonal. You may have to take my word for it that VI is always going to be an outward pointing normal vector. So for a particular edge vector, there's only two directions I could be going in that are orthogonal. And this is, I'm just waving my hands and saying it's definitely going to be this one. And you could verify that in all sorts of different ways. But as far as how I got the formula, if you consider the way you would apply, let's say, a rotation matrix or something, or you could use complex arithmetic, this is what you'd get out of a 90-degree rotation. Okay, so I have this vector VI, but because of the way that I derived each edge vector, EI, the length of the edge vectors is going to be the length of the edge itself. What I'm going to end up wanting is a unit normal vector. So I have these normal vectors, so here's E2. The normal vector that I created, V2, is going to be really long because E2 itself has a large length. What I'm going to want is to have every normal vector that I construct have the same length, and it's a lot easier for so many different reasons to have that length be 1. So what I will do is I will define n sub I to be the unit normal vector for edge I. And I compute that by taking v sub I and dividing it by its own length, as we're used to. And there it is. There is that creepy square root sign and actually some squares that we know are anathema to a linear program. But you'll notice nowhere on this slide am I doing any linear programming. All I'm doing is defining vectors. Eventually, I'm going to use these vectors once they are computed as input to a linear program. I'm going to construct a linear program using the components of this vector ni. But I'm allowed to do whatever computations I want before I actually construct a linear program. Ni is constant in the context of a particular instance of this problem. You provide me a list of points, I could then compute Ni just by doing a bunch of arithmetic using those points. I don't need linear programming to compute it. So by doing this, I'm offloading that distance calculation into this pre-processing step. So I'm allowed to do this. And in general, this is valid. In an application of linear programming, you're allowed to do whatever weird nonlinear stuff you want before you construct a linear program. You have to make sure, though, that when you actually define an optimization problem, that all of the optimization variables are treated in a linear way, that you're only working with linear functions of those optimization variables. Okay, so I end up with this. I end up with this set of unit normal vectors, one for each edge. Now I want to spend some time on some commentary about why this is helpful. And what it has to do with is, if I choose a particular center point, what does it mean if I consider a particular radius for the entire disk of that radius to be inside the polygon? So with respect to a certain center point, certainly I guess it means that if I look at if I actually draw the disk, I don't want any part of the disk sitting outside the polygon, obviously. And we normally can think about that as, okay, that looks like there's an infinite number of points I have to consider, every possible point around the disk. But because it's a convex polygon, which comprises a finite number of these edge segments, it turns out I can use some geometry to avoid actually having to check the majority of points. I only really have to consider the closest point to my center point along each edge. So I know that if the closest point is within my radius, so here's, suppose I choose this as my radius. If I walk towards a particular edge in the most direct possible direction, and the point I end up at once I travel the distance of my radius is still inside the polygon, then no other point along the edge will somehow be inside the disk. The disk will be entirely contained behind this half space here. And I've got a few diagrams to sort of justify that. Before I do that, I want to talk about what it means for a point to be actually on a particular edge. So let's consider this point Q. So this point Q lies on the edge between P0 and P2. So this would be edge number 2, because we consider them in the clockwise traversal. This would refer to this normal vector N2. So what does it mean for a point to actually be on an edge? And here's where all the training we've had into interpreting linear constraints can come in handy. We know already about what it means to define a half space. And in fact, if we think about this polygon as the intersection of half spaces, the interior of the polygon will only contain those points that are on wow, that's a bad line, that are on this side of the line. And it's, of course, the intersection of multiple half spaces. And so we actually already have some knowledge we can apply here. For a point to be on the line, well, we know this is the normal vector of the line. And so it shouldn't surprise us that for a particular point, I'm going to call it R for this, what I'm just drawing here, for a particular point R to be on or behind this line here, we would want R dot N2 to be less than or equal to, I don't know, some constant C. Let's not use C for this, let's use D. Some constant D, and we don't really care what that constant is, but we should be familiar with this equation to define all of the points that are on or behind that particular edge. We also know that for a point to be actually on that edge, we would want this constraint to be met at equality. Okay, so where does this come into it? Well, let's consider then a point Q that's actually on the edge. So Q dot N2 equals D. We know that P2 and P0 are both also on this edge. Basically, by definition, we've defined the edge to be the line segment between P0 and P2. So we know that P0 dot N2, draw the vector hat here, is also equal to D. It's also on the same line, and so is P2. And notice that although the point Q is just some random point, P0 and P2 are part of our inputs. They're constant. And so if I'm asking, hey, what's the value of D? Well, wait a minute. Here it is. P0 dot N2 equals D. So Q lies on the line if Q dot N2 equals P0 dot N2, or if it equals P2 dot N2. I could use a point that is known to be on the line to figure out the value of this constant. That defines the line. And that's what I'm saying here. If I look at any particular edge, not just P0, P2, but any particular edge, edge I, the set of points actually on that line must have this property. And again, notice that everything over here is fixed. It's part of my input. It's the points and these normal vectors that I already derived. Additionally, if I consider points that are inside the polygon, and this is an extension of what I just said, if I consider all the points that are inside the polygon, any point that's in the interior, so some point R, has to be inside the half space defined by each of these edges. And therefore, we already saw how we defined that half space before using these normal vectors. I need to have any point R observe this constraint for every single edge. So not just obviously for this one, but also for this edge here and for this edge here. Any point that meets that constraint is in the interior of the polygon. And that's an observation that should be dead easy for us by now, because we've spent more than a month essentially talking about the implications of that. It's the same as the question of feasibility for a 2D linear program. And then there's this. And this is the place that we're able to eliminate that distance calculation. So let's consider a center point C. Sorry for not labeling the diagram properly. Let's consider some particular center point C. It doesn't matter where it is. I just choose any, we'll assume it's an interior point, but I choose any center point C. And the question is, if I go looking for a point along one of the edges, but I guarantee that I only walk in a direction that's definitely parallel to the normal vector. So I'm going to start at my point C, and I'm going to walk towards edge 2 in the direction of N2, in the direction of that normal vector. And of course, if I do that, and I start at the interior, I will eventually hit the edge. So I'll end up at this point Q, well, it's drawn there, equals C plus, well, I walked in this direction, so what I end up doing, I guess I'll draw that out. This is equal to D times N sub, this will be N sub 2. Okay, so I start at C, and I walk in this direction, in the direction of N2, for D units. So I multiply N2 by D. The question is, how far away from my center point C is the point Q? What is the distance from C to Q? That's the question. And usually, of course, that would require some kind of square root. However, if we stare at this for a minute and we use what we know about distances and points and vectors, we actually can figure out that the distance sort of falls right out of the equation. It turns out to be this number. And I can give a brief justification. So what is the distance from C to Q? Well, it would be this distance here. So it would be Q minus C, treat it as a vector, take its length. Okay, well, let's expand that out. That would be, so Q is defined to be C plus dNi. Well, in this case, it would be, well, let's use dNi. And then that's all minus C. Okay, and then if I simplify this a bit, what I realize is that I'm actually just looking at this. And D here is a scalar. I've just multiplied my normal vector by a scalar, and I can remove that. I can pull that right out of my distance calculation. And then we observe that because of the construction of our normal vectors, our unit normal vectors, this thing here just equals 1. So that means this equals D. So I was able to compute the distance as long as I'm only moving away from my center point parallel to the normal vector of an edge. I can compute that distance without needing a square root. It's just sort of falls right out of the calculation. Okay, so the next question is, why am I only going to worry about that particular type of construction? So I'm starting at my center point, and I'm walking towards each edge in a direction parallel to its normal vector. And the reason basically is that what I want to consider is, what is the closest point to my center point C along any particular edge? Because if the closest point along a particular edge is greater than or equal to the radius of my disk, then the disk is not going to somehow exceed the boundary of that edge. I think the next slide, yeah, the next slide defines that. So the closest point for a particular center point C, the closest point from C to a particular edge will always be the point that you obtain by walking in a direction orthogonal to the edge. In other words, in the same direction as the normal vector. Okay, so can I give a brief justification of that? Well, how about this? Here is the closest point along the direction of the normal vector. We'll call that Q. Suppose that there were a point that was closer that was somewhere else. Okay, so we know that because this direction we walked in is orthogonal to the line, it's along the normal vector, this has to be a right angle. Okay, so suppose the closest point was somewhere over here. We'll call this R. Wait a minute, though. This is a right triangle, isn't it? So if I can consider the point CQR, that's going to be a right triangle, and this is the hypotenuse of it. And that means by the Pythagorean theorem, this is going to be at most the same length as the hypotenuse. I mean, it could be degenerate. R could be equal to Q. But otherwise, R will be further away from my center point than Q is. And that's the basic logic. Because the normal vector is perpendicular to the edge, I'm guaranteed that the distance along the normal vector from C to the edge is going to be at most equal to the distance from C to any other point along the edge. So the closest point on the edge will therefore always have this form. For any particular edge, the closest point with respect to the normal vector of that edge will always be defined this way, with some choice of center point. And that actually gives us enough, because we now know that because this is the distance from my center point to that point Q, all I have to do is to make sure, if I've chosen a particular radius R, that the radius that I'm using is less than or equal to the distance to that closest point. And so I end up with this, and I'm gonna do some of this algebra, but some of it I'm just gonna skip over because it might be obvious. But basically, what I'm saying is I have these three variables I care about: my center point, so Cx and Cy, and the radius, R. Okay, and I want to make sure that the radius r, if I start at my center point C and I define some disk around it, okay, there we go, there's a better center point. If I define some disk around it, and it's got this radius r, that of course does not exceed the bounds of the polygon. For now, I don't even care that it actually touches the inside of the polygon. We'll use the optimization to figure that out later. What I care about is finding a way to define constraints that ensure that no part of this disk gets outside the polygon. So what I want to do is I want to make sure that if I consider the center point and then I consider any particular edge, like this one, that the closest point along that edge is definitely further away, or at most the same distance away from the center point as the radius that I've chosen. Okay, so that means if I apply what I've just seen, because I know how to get that closest point, I can then define this set of constraints. Okay, so I'll clear this. So the first thing is I end up with this equation here. So this is to say that if I start at my center point C and I take a particular normal vector and I walk r units along that normal vector, r times n dot I, that the point I end up at still has to be inside the polygon. So we know how to define that a point is in the polygon, so we saw that earlier. A point is in the polygon if this holds for every edge of the polygon, so each edge I. So I want this, C plus R, so this is C here. C, and then this point here would be, I'm not going to use an arrow, we'll just say this is equal to C plus R times Ni. I want to make sure that this point is still inside the polygon for every edge normal vector. And the equation that I end up with is this one. C plus R times Ni dot Ni has to be less than or equal to Pi dot Ni. There's a lot going on here, but observe, this is all constant stuff. I could pre-compute this dot product. And Ni is, once I've computed it in advance, it's also constant with respect to the optimization variables. And then same here. So if I do a little bit of algebra, if I distribute these brackets here and I expand some stuff out, I end up with this. And then we consider, what do we have? Well, okay, Ni dot Ni, well, we know that any particular vector v dot itself will give us the length of v all squared. And we know that Ni is a unit vector, which means Ni dot Ni is equal to the length of Ni all squared, but the length of Ni is 1, so that's just 1, which means this whole term just disappears. We don't care. It's just multiplying by 1. C dot Ni, well, Ni is a constant, and it turns out that dot products themselves are linear functions, so even if it weren't, it wouldn't be, well, yeah, okay. Even if it were, it might be a problem, but in this case, Ni is a constant, and again, the right-hand side is a constant. And so if we expand that all the way out to remove the vector notation, we get this. And if we stare at it, we'll notice that is a linear constraint. Here, where I appear to be multiplying together pairs of variables, these are just multiplying together constants that I was given. So it's easy to do that. I can do that before I provide my LP to the solver. And then this is a constant, and so is this. And so for my optimization variables, as far as they participate in this constraint, they are participating in a linear function. So there we go. I've got this linear constraint that I can define for each edge I to guarantee that if I start at my particular center point and I walk towards that edge for this distance R, that I stay inside the polygon. And so if I just package all of that together for every possible edge, I end up with this linear program here, which is not in standard form. And we'll learn in this course that once we get into talking about applications, we often see LPs that are not written in standard form. And we only care about standard form because we know any LP can be put in standard form, and because if we want to make up a simplex dictionary, we of course need it to be in standard form. But this is not in standard form. So what I've done here is I said, what I want is for, if I start at my center point and I walk towards any edge for a distance of r, the point I end up at has to still be inside the polygon, no matter which edge I'm talking about. The point I end up at has to still be inside the polygon. And then I want to maximize the value of r. I want the largest radius that still gives me those guarantees. So that's why I have this relatively simple objective function. Now the reason it's not in standard form is you'll notice that Cx and Cy are unconstrained. And that's for a pretty practical reason, which is that if I hand you a particular polygon, Who's to say that the polygon doesn't have coordinates? Like, what if these are my x and y axes? What if my polygon is sitting somewhere where vertices have negative coordinates? Well, that means that my center point could have negative coordinates. And therefore, we shouldn't, in general, constrain cx and cy to be positive. We should constrain the radius to be positive because it doesn't make much sense to talk about a negative radius in this context, or in many contexts, frankly. But because we don't know anything about the coordinates of the vertices, we should allow cx and cy to go negative. Now, on the assignment question about this, you'll notice that I added a proviso at the end that says because all of the vertices are, as it turns out, they have positive coordinates. In that case, if every vertex does have positive coordinates, so here's some vertices, if I tell you that all of these have positive x and y values, you know the center point has to be somewhere in the middle of them, and therefore the center point will have positive coordinates as well. So on the assignment question, you actually are allowed to enforce the constraint that cx and cy are greater than or equal to 0, so that you don't have to do as much work to put things in standard form. Because if these two variables are unconstrained, as you know, putting it in standard form can be a bit ugly because you have to do that variable doubling substitution, which is a bit of a mess. So this is a linear program. What we've ended up with is linear. We did a lot of weird stuff to get here, all of it pre-processing, all of it tedious but mechanical, so straightforward. Once we were done, we had an optimization problem that we can feed right into a linear programming solver, even though the fundamental application seemed really, really nonlinear. It involved circles and Euclidean distance. And we'll see something else, something very similar to that, where we're able to avoid distance calculations by being clever in the next application. But I think what I'll do is make that a separate video and then take a break in the middle.